Early in our study of fluid mechanics, before we become concerned with the motion of fluids, it's important to understand pressure and the forces that pressure exerts on solid bodies. To begin, we need instruments that measure pressure. This tire gauge, based on the Borden tube principle, reads the tire pressure as a gauge pressure, about 34 pounds per square inch, psi, or 234 kilopascals. Gauge pressure is the increment of pressure above atmospheric pressure. This is another instrument based on the same principle, but designed to read absolute pressure. It reads about 14.4 psi when open to the atmosphere at the altitude where these experiments were done. If we apply pressure above 1 atmosphere, the reading increases above 14.4 psi. As a vacuum pump draws the pressure down, the reading tends towards 0 on this absolute pressure scale. Both these instruments operate on the Borden tube principle. The curved tube is connected to the high pressure being read. A higher pressure tends to straighten out the tube and vice versa. The end of the tube is connected to a linkage that drives an indicating needle on the face of the pressure gauge. There are other instruments to measure pressure, such as this diaphragm-type transducer. A pressure difference across the thin metal diaphragm causes it to flex and changes the internal capacitance of the transducer, which is sensed electrically and converted to a pressure reading. This is a modern piezoelectric pressure transducer. Its tip contains a crystal that responds to pressure changes by generating an electric charge. The amount of charge can be converted to a pressure reading through calibration. Hydrostatic pressure increases linearly with depth in a fluid. You can feel the pressure increase just by diving to the bottom of a swimming pool. Hydroelectric dams must be designed with this in mind. They're much thicker at the bottom than at the top in order to withstand a large increase in hydrostatic pressure. The water enters the hydroelectric turbine at high pressure from the bottom of the dam and retains enough kinetic energy to produce a water jet when discharged at 1 atmosphere. Watch the colored pressure contours on the supporting columns of this oil rig CFD simulation. As the water level rises due to waves passing, so does the pressure level on the columns. Deep-sea research craft like the Johnson Sea-Link submersible must be made immensely strong to withstand the pressure at the ocean floor. This doesn't bother the strange creatures that live there, however, because the pressure inside their bodies is the same as the surrounding pressure. If that were not the case, they would be crushed instantly. Here's a popular little experiment that demonstrates hydrostatic pressure in the atmosphere. We boil some water in this metal can, then cap the can and sit it in cold water. As the steam condenses back to liquid inside the can, the internal pressure drops and the can is crushed. It's tempting to think that the sides of the can are sucked in, but in fact, the can is crushed by the weight of the column of air over 100 kilometers high that sits on top of it.